Other than that, we're going to get started with our activity for today. We've got a Desmos activity to help us practice the new concepts we learned about section 7.1, sampling and distributions yesterday in class. So I'm going to give that link to you guys so you guys can join that activity. And so that is popping up in the chat, hopefully. All right, and we should be sharing my screen now, so that's good. So here we go. I'm going to open up the first two actual questions. They're both card sorting questions. The goal of these two is to properly sort the term with the definition in the first set of cards to match up. And in the second one is to match the term with its appropriate context. I do find it to be helpful to kind of line things up so they're not so scattered. So put like terms at the top and you can move the other ones so that you can see them all. All right, when you match the terms, it is, in order for it to actually know that it's matched, you have to wait for the one behind it, behind the one you're clicked on, to highlight. Then when you let it go, it will pair them together. If you just put them close, it won't, it's not going to register that they're paired up. All right, so please make sure you do that when you're ready. All right, so we're going to do that. First one is matching term with definition. Second one is matching term with context. And yes, I know there's a typo in this problem. I keep meaning to fix it and then I keep forgetting. Alrighty. So let's talk about these. So if you like, please switch over so you can see my screen. That would be excellent. So we're going to look at statistic, parameter, population, and sample. Oops, sorry. First one, we have parameter, sample, statistic, inference as our vocabulary terms. Remember, parameter and statistic go along with population and sample. All right. So the first one, parameter, is a number that describes some characteristic of the population. And remember to make sure to get the cards to pair, you must wait for one of them to highlight. Then they pair up nicely like this. The sample is a subset of a larger population. The statistic is a number that describes some characteristic of a sample. And finally, the inference is an estimation of a characteristic of a population using sample statistics. All right. Is there any questions about these terms? Okay. So then next we have the business owner. And they want to know the average household income in her business zip code. She randomly samples 80 households in the zip code and finds their mean income to be $46,144. The statistic is X bar, the mean income of the sample, statistic sample. The parameter would be mu, that would be the mean income of all households in the zip code. The population, all households in the zip code, and the sample is the 80 surveyed households. So that's how these terms apply to our context here. All right. So is there anything I can clarify about these terms and how they go together? Then we are ready to move on to the next question. So we're going to move it on to screen number 4. This is a sampling distributions. A sampling distribution is the distribution of statistics from all possible samples of the same size from a population. Note, sampling distributions are made of statistics, means, proportions, quartiles, etc., not data points. Right? And also note, the statistic will not always be the mean from your sample. It might be a standard deviation, it might be a quartile, it might be a variance or a range or something like that, right? It's just a statistic, something you're measuring from your sample. Right? We have the sampling distribution simulation, right? This simulation estimates and plots the sampling distribution of various statistics. You specify the population distribution, sample size, and statistic. An animated sample from the population is shown and the statistic is plotted. This can be repeated to estimate the sampling distribution. So we're going to look at this guy here. There's instructions here. You're welcome to read them if you like. There's a link to this simulation in Canvas if you'd like to access it at some other point in time. We're just going to look at the actual simulation here. Right, so we have our parent population in the first histogram. Right now we have it set as normal. We could go skewed if we want. We can make up our own. Right, that's all kind of all over the place, right? We're just going to stick with normal for now. The next histogram will represent our sample data. All right. And right now, here we'll do both of these there. The next two will give us a distribution of means. All right. I could set one to mean, one to median. Could do standard deviation, variance, right? There's a couple other things, range. We'll just do those. And n equals 5 on these. This is the sample size that these statistics are based on. All right, so I can set 1 to 5, and we'll set this one to 20. So this third histogram will be based on a sample size of 5. The fourth histogram will be based on a sample size of 20. Right, and we can run this sample data. Right now it is set up to simply, if I hit animated, it will run one sample for each histogram. So the second one that's running is the 20, and it's going to drop us one data point for our sampling distribution. I could click 5. Right, and instead of doing the animation, it's just going to spit out the numbers for me. So right now we have, based on 6 reps, because it kept the first one I did for each of them. So 6 samples. I have the mean of 11.63 here, median, standard deviation, right? It's tracking the mean. This one's the median. Notice they're not very similar at this point. I do not know what kurtosis is. I need to look that up. Someone asked yesterday, but yeah, or not yesterday, the day before. So this gives us an idea of what's happening now. Obviously, over just 5 repetitions of this, 5 samples, it doesn't give us a ton to work with. So we have these nice little buttons here. It does 10,000 or 100,000, right? We'll just go ahead and do 10,000 samples real quick. So we've done, in the third histogram, 10,000 samples of sample size 5. And on the fourth histogram, we've done 10,006 samples of sample size 20, and that's giving us the median. All right. Now, to do a better comparison, I'm going to have both of these do the mean. We're going to do sample size 25 for one and 5 for the other. We're just going to push through 100,000 repetitions. Notice that the third histogram here is much more varied than the fourth. Right? This is a very clear illustration that the larger the sample size, the smaller the variance is. That was one of the things we learned yesterday. All right, we can also see how normal both of these curves appear. And they both seem to be good unbiased estimators, right? They're pretty accurate to the actual mean. And so those are good things. Right? We would consider this, the fourth sampling distribution, a little bit more accurate and a little better because it is less varied. So this is kind of how we can use this guy here as a nice fun simulation. Let's just see what's going on. So now we'll jump back into Desmos here and we will answer this question. What do you notice and what do you wonder about the sampling distribution? And again, you're welcome to click on that link. It should be active within your screens as well. And if you want to take another look at that simulation, you're more than welcome to. We're going to take just a few minutes here to answer what you notice, what you wonder. Please just one thing for each of those. One noticing, one wondering. It doesn't need to be a big list. Been reading through a lot of you guys' responses to this. Some of these questions will be answered throughout this course, through the remainder of the course. Some of these questions we can answer right now. So let's see. One of the questions or one of the wonderings is, I wonder if we put an outlier in the data, how would the distribution look? Depending on how severe the outlier is, it could skew the data. But again, that's also why we're using the sampling distribution and not just the sample, right? So the sampling distribution kind of helps account for a possible outlier in a sample. Because if you think about it, if we're only introducing one or two outliers, chances are those probably occurred in different samples, which means they affected one of our sample statistics, which then becomes one of our data points in the sampling distribution. And overall, that kind of skewness gets accounted for as all these averages kind of build into a normal curve over lots of samples. So the likelihood of getting a sample statistic that is skewed probably would indicate that your sample was biased to begin with. Right? That particular set of sample data to get a completely skewed average or skewed mean or whatever statistic you're tracking was probably a biased sample, in which that case you probably consider not including it in your data. So that's what I have to say about that. And so wonder what the simulation can be used for calculating. The simulation isn't really going to be able to calculate stuff for us, unfortunately. It gives us a visual representation of what this could look like. It's possible we could try to really finagle it and make it fit into like certain parameters of like a problem in a specific parent data set. But it's more just a simulation that allows us to see how this process works. Another one here. I wonder how you can get your correct distribution. Distributions aren't inherently correct or incorrect. They could be biased, or they can, be largely varied for some reason. But data is data. It can't be correct or incorrect. It just is what it is. So if your distribution doesn't look like it should, that could be an indicator that you had a biased sample, or that what you're sampling doesn't have a reasonable statistic for that. Like it might not have a reasonable mean. People might be too different, so to say, or too varied in their opinions, right? Be on other sides of things. So yeah. I wonder how small a sampling distribution can be until it is no longer accurate. So I guess the easy answer on that is that if a sampling distribution is only based on one sample, then it's really just whatever you got from that sample, and we know that samples can vary. So the more sampling you can do, the more sample sets of data you get, the more accurate your sampling distribution should become to, or the more accurate it gets to the actual values from the population. If you're only doing 1 or 2 samples, you probably don't have enough data to make an inference about the entire population, which is the goal. So that's some of the questions. Yeah. So I lost someone else who dropped out of here. Oh, all right. So we're going to move it on to the next 2 questions. So we'll go here and there. All right, so the next 2 questions here. All right, we've got sample or sampling. All right, so we're kind of looking for, in your own words, the definition of these 2 terms. Right, a sample distribution is something, and a sampling distribution is something else. They are related, right? And there's an image here to the left to kind of help you see the visual difference, which is kind of based on the simulation we did. So kind of in your own words, and you may want to look back at some of the things that you have in your notes from yesterday. What is a sample distribution? What is a sampling distribution? Right. Then the next question, the second one you have access to, is accuracy versus precision. And you need to answer the question, how do you avoid bias and how do you reduce variability? And we want to answer these questions based on the context of this chapter. And please just provide 1 way to avoid bias and 1 way to reduce variability. So let's see what we have here. All right, so for this first one, sample or sampling, right? A sample distribution is the data, right? Is essentially just the data collected, or the distribution of the data collected from a sample, which is a subset of the population. It's from a single sample. And it could be, in this case, they're tracking incomes, so they just collected data on everyone's income in the sample. The sampling distribution, right? That is, it should be the collection of all possible samples of the same size from the population, right? And it should be a statistic, to help understand and hopefully make an inference from that. And so it's a collection of a statistic from the sample sets. In this case, it's the means of the incomes from each sample set of data, right, on this example. Okay, so they're very similar, and the fact that their wording isn't very different can make it difficult. So you want to look for like singular verbiage. Sample distribution is from a single sample of data. Sampling distribution is a collection of some statistic from all of my sample sets. All right. Is there anything I can clarify on sample or sampling distribution? All right, and so as far as avoiding bias and reducing variability, one of the basic ways to avoid bias is to sample randomly. Make sure you're doing a simple random sample. If you're taking random samples from your population, it's the best way to avoid bias. One of the best ways to avoid bias. There's other things we can do to avoid bias that we were discussed, hopefully, previously. And then on reducing variability, this just ties into what we discussed when looking at our simulation and in the lesson yesterday. To reduce variability, we increase the sample size. Right? Larger sample sizes reduces variability. And those are just one way for both of these here. Okay. Is there anything I can clarify about this question? Okay, excellent. So we're now going to move on to the next two problems. So now I'll shifting over to screen 7 or slide 7. Both of these problems have the same directions. Okay, so the Arizona iced tea and then the New York to Denver, which is the next slide, says each boldface number in the context below is the value of either a parameter or a statistic. Choose which each number is, and then select the appropriate notation to describe the number. And so you have a context to read here. This one's about Arizona iced tea. You'll have another context in the second screen on New York to Denver flight. In each, you're given 4 choices for the parameter and 4 choices for the statistic. You need to select the appropriate checkbox that correctly pairs the parameter with its variable and value, and then the one checkbox that correctly pairs the statistic with its value and variable. That is the goal. So you should have one check mark next to a parameter and one check mark next to a statistic, total of 2 check marks per question for each of these next 2 problems. All right, and I realize that may not have been enough time for everyone to finish both the problems, but that is okay. We're gonna talk about these real quick. So back on the Arizona iced tea problem, we're given the context that on Tuesday, the bottles of Arizona iced tea filled in a plant were supposed to contain an average of 20 ounces of iced tea. Quality control inspectors sampled 50 bottles at random from the day's production. These bottles contained an average of 19.6 ounces of iced tea. So we have the bold numbers 20 and 19.6. 20 is a parameter. That's our average for the population. All right. And so that will be this in my screen. It's the first checkbox that is parameter mu equals 20 ounces. The next number, 19.6 ounces of iced tea, that is the sample statistic. Right, so that gets the statistic X bar equals 19.6 ounces. Right. So something you might want to remember is that the statistic gets the special kind of notation, right? It gets X bar, and the next one we'll see P hat, right? Parameter will get a more normal variable, or possibly the Greek letter that's normal. It doesn't have any extra notation attached to it. It's just like mu, all right? In the next problem, on a New York to Denver flight, 8% of the 125 passengers were selected for random security screening before boarding. According to the TSA, 10% of passengers at this airport are chosen for random screening. So that first number, the 8%, is the sample statistic. It is from our sample of 125 passengers. So that will get statistic P hat, right, proportion, so we're using P, of 0.08 or 8% of the sample of passengers. So that is down here. The 10% is for the population. That's what it's supposed to be. That's the the actual value, right? So we should have parameter P equals 0.10 or 10% of passengers. Because in this case, our population is passengers that go to this airport. I clicked the wrong box. That's the one. All right. Is there anything I can clarify about these two examples? Last thing is I'm opening up the last 3 slides. All right. We have 2 problems dealing with our orange M&Ms. All right, so Mars Incorporated says that the mix of colors in its M&Ms, milk chocolate candies, is 24% blue, 20% orange, 16% green, 14% yellow, 13% red, and 13% brown. Assume that the company's claim is true. We want to examine the proportion of orange M&Ms in repeated or random samples of 50 candies. We're going to identify the individuals, the variable, and the parameter of interest. So that is the first question. Second question. Which of the graphs that follow could be the approximate sampling distribution of the statistic? Explain your choice. I do apologize. I could not get these images to be any bigger. The first image shows a bar graph. The second image shows a dot plot. In the middle, it goes a range from 0.00 to 0.40. Right. The third dot plot goes from 0.20 to 0.60 as far as its range. Right, so you need to choose between these 3, which one could be an approximate sampling distribution for the statistic we are tracking, right? Proportion of orange M&Ms. And the last one is a few multiple choices to make, having to do with these 3 histograms. Right. So I'm going to give you all 5 minutes to work through these 3 problems. That may or may not be enough time to answer all 3 of them. After that, we'll talk about it, and then that'll be the end of our day. Alrighty. So here we are. I'm going to jump back to the first question here on our orange M&Ms. We need to identify the individuals, the variable, and the parameter of interest. All right. In this example, individuals are M&Ms. And those are the things we're collecting data on. The variable is color. That's what we're tracking, the color of the M&Ms. That's what we're interested in. The parameter of interest is the proportion of orange M&Ms. That's our individual variable and parameter of interest. Is there anything I can clarify for this question? The next question, which of the graphs that follow could be the approximate sampling distribution of the statistic? Right. The first graph is a bar graph. Right. That means that it's not necessarily the type of distribution we're looking for. This bar graph simply shows the results of a single sample. Right. It doesn't tell us the proportion of any single color. Just tells us the frequency. So in this sample, we had 18 blue, 8 brown, 14 orange, or not 14 green, 10 orange, right? So it's just the results of a sample, a single sample. The second and third are both dot plots, which show that they are a collection of the proportion of orange. They're both p hat. The one in the middle could be the approximate sampling distribution for our statistic of proportion of orange because it has a mean or a center of 0.20, which corresponds to the 20% orange that is the actual proportion from our population. So the second dot plot here, or the first dot plot, second graph in this set, is the approximate sampling distribution for the statistic, or could be. And then here, anything I can clarify on this example? All right, our last one, we have histograms of the values taken by 3 sample statistics in several hundred samples from the same population. The true value of the population parameter is marked on each histogram. So the small arrow at the bottom is showing what the true value of the parameter is supposed to be. So which statistic has the largest bias among these 3? That would be histogram C. Right? This is because it is obvious that the center of histogram C is not where the true value of the parameter is. So it's showing bias. It's kind of like on the bullseye where we have a kind of a clustering of things that are off center. Right? Which statistic has the lowest variability among these 3? That would be A, as it is the skinniest. It has the smallest range, so it has the least variance, least variability. And then based on the performance of the 3 statistics in many samples, which is preferred as an estimate, again, that would be A, and that is because it has the least amount of bias and a least variability. And that's what we want. We want no bias if possible, and as little variability as possible. And so that is what A is giving us.